I'm going to walk you through the steps for calculating a z-test. In this example, we have a population distribution, and the mean for the population distribution is 500, and the standard deviation is 150. So here's a drawing of the population distribution with the mean of 500, standard deviation of 150, and every value here represents an individual score. Down below, we're going to have a distribution of sample means. For a distribution of sample means, every sample will consist of 120 values randomly selected from up above, and then its average recorded down here below. So up above, I've gone ahead and indicated 120 dots here, and they would represent our sample size. And from those 120 dots, we would get one sample mean. And that sample mean would then be recorded here for a distribution of sample means. So 120 values, that sample mean is going to be a really good estimate of the population mean. We expect to be pretty close to 500. Well, just how narrow is going to be this distribution of sample means? To do that, we're going to use our formula. So here's our equation to tell us just how much variability there's going to be in our distribution of sample means. We refer to it as a standard error. It's just like the standard deviation for a population, but we call it standard error when we're dealing with the distribution of sample means. And it's going to be the standard deviation divided by a square root of n. So we put 150 in for our standard deviation, and we put 120 in for our sample size. The square root of 120 is going to be 10.95, so we have 150, the standard deviation, divided by 10.95. And that's going to give us a standard error of 13.70. So whereas in the population distribution, these scores widely vary around the mean of 500, the standard deviation is 150, that's really huge. Because each of our sample means is going to be the average of 120 of these scores, they're not going to vary as much. 68% of them will be within plus or minus 13.7 around that value of 500. So again, to give you some comparison, from the empirical rule, you remember that 68% of the values are within plus or minus 1 standard deviation. So 68% of the individual scores are between 350 and 650. Well, when we're looking at our distribution of sample means, 68% of sample means will be between 486 and 513 plus or minus 1 standard error. And again, it's because every sample mean is going to be a pretty good estimate of the true population mean, given that it's based on 120 scores. It's going to be really unusual to get 120 scores, for example, that are all around 650. That would be extremely unusual. Now, for our sample problem, we're told that the sample mean is 625. So just think, a sample mean is 625, and here's our context. The mean of all these sample means is 500, and most of these sample means are between 486 and 513, and this is going to be at 625. At 625, you can see that it's really out there. I mean, 625, if it was just an individual score, not that unusual. But 625, when it's the average of 120 separate scores, that is extremely unusual to get 120 scores that are all average at 625. So let's calculate the z-test, because the z-test is going to tell us how many standard errors 625 is away from the population mean of 500. Just how far out there is this value of 625 as a sample mean. To help us out, we have our z-test formula, where the z-test is equal to the sample mean minus the mean of all the sample means, basically the population mean, divided by the standard error, and we calculate the standard error over here. So our sample mean, 625, minus population mean of 500, divided by the whole quantity, divided by the standard error of 13.70. I'm going to make this more accurate. I'm putting parentheses around the sample mean minus the population mean here, just so that you know that it's sample mean minus population mean, and then you divide the result by the standard error. So here we have written out quantity of 625 minus 500, and that quantity again divided by 13.70. That's 125 divided by 13.70, and that equals 9.12. So what that's telling us is that a sample mean of 625 from this distribution of sample means, where the average is 500 and the standard error is 13.7, is incredibly rare. That sample mean would be 1, 2, 3, 4, 5, 6, 7, 8, 9.12 standard errors out. Keep in mind that whenever you get a z-score or z-test of like 3 or -3, you know, if it's like more than 3 standard deviations or standard errors away, the probability of that happening to the chances is really small. So if it's 9 standard errors out there, we've got a better chance of getting hit by an asteroid in the next 5 minutes and the Earth blowing up than we do of this happening again anytime in someone's lifetime. So that is to say, it'd be extremely unusual to get 120 scores whose average was 625. Up above, I've shown you what it would look like to randomly sample 120 scores whose average was 625. It would look very much as if we were sampling from an entirely different distribution. Probability of getting this from a population that has a mean of 500, standard deviation of 150, getting all these scores all pretty much above the mean. I mean, think about flipping a coin, heads or tails, and getting it like tails time after time after time after time, hundreds of times in a row, so to speak. You're looking at less than like 1 in a trillion probably of getting a sample like this. So that's why we calculate the z-test. We want to know how many standard errors is our sample mean away from the population mean. We did the z-test, we got 912. We asked that question to ask how unusual would it be to get a sample mean of 625 from this distribution of sample means where the mean is 500 and the standard error is 13.7, right? How unusual is a sample mean of 625? And again, sample size 120. And what we've learned is it's extremely rare. Z-test of 9.12, probability incredibly small there. All right, so that's our answer. That's why we do it, and that's what it looks like. Take care.